नहीं नहीं
Dr. Aneesh professor ExCom member and ACU at NHR. He has done his PhD on data analytics and ML from University of Technologies and MS by research in the CSE IIT Hyderabad and BTech EC from JEE. Triple IT Hyderabad and BTech EC from JEE. He has 4.5 years of experience in R&D and 3 years as academia and 7.2 years experience in the industry. So now I request Dr. Aneesh to take over the session. Thank you, sir.
I'll give an introduction to both machine learning and deep learning before looking at the cybersecurity applications, because there are many applications. I'll take some examples, and I've put lot of content into the slide, so hopefully that's helpful to you. Okay, so we want to go through the introduction before that. So I too work in the BITS Pilani Hyderabad campus. Earlier I was in Australia and I was working on several industry and government projects. Before that I did a PhD there, and before that I was working in IIIT Hyderabad. So I have been working in machine learning for several years, and in the computer science department we want to set up collaboration with external faculty or students. So please feel free to contact us for any research collaboration, project collaboration, so on. Okay, I think I'll talk from here. So we want to understand machine learning, then we want to see motivation for deep learning, and then I'll introduce a topic called adversarial deep learning, which is the state of the art in deep learning. These are all basically different types of algorithms and ways to design them, and one has to map these designs to the application scenario which is available in cybersecurity. So I've taken some examples, but there's a whole list of applications which one can explore. So starting with these slides are divided into these topics, so wherever I change the topic I'll let you know. So let's try to understand what is machine learning. So when we try to look for the different terms associated with machine learning, maybe go on Google or search in our phone, we come up with all these terms such as nonlinear transformation, neural networks, noisy targets, perceptrons, weight decay, regularization, so on. And we don't know where all of them fit together. So this is the first thing one has to understand, the technical terms and the meaning associated with them, and what sort of categories can we put them into. Here I have a mind map where one can work either on the algorithm side, which is either analysis or design of algorithms, or one can work on the theory side, which is more mathematical theory. One can understand machine learning as linear algebra, probability theory, graph theory, so on. And one can look at the applications such as cyber security applications, and from there build models. There are so many kinds of models: linear, non-linear models, support vector machines, neural networks, graphical models. Once we build these models, we're going to so-called train an algorithm. There's going to be an algorithm learning something, some pattern, parameter from the data, and these are all the algorithmic techniques which we have to understand, such as how to create the input data for the algorithm. And like Paresh was saying, we can put them into different paradigms of machine learning, different types of machine learning, starting with supervised learning. Because what is it we want to look, what is it we are learning? If we know that, that is called supervision, and we can express that as set of discrete labels, and any variation of that, such as unsupervised learning where we don't have labels, semi-supervised learning where we have some labels, or reinforcement learning like what he described, or other learnings like online learning, active learning, continual learning, all of these things. So we have to understand what is learning, and then these different types of learning, and then map it to some algorithm and model, and have some kind of theoretical understanding, preferably. Otherwise somebody else will do the thinking for us. So here this is not legible, but this is basically a mind map of techniques from scikit-learn, which is a Python library. And it is, so this is machine learning, knowledge representation learning, and this is automated planning, this is natural language processing, multi-agent systems, robotics. So in all of these categories, when we get into machine learning, we have supervised learning, semi-supervised learning, unsupervised learning. So similarly, if we get into, let's say, supervised learning, we have classification and regression. In classification, we have artificial neural networks, instance-based learning, kernel methods, decision trees. So this is what the package of Python implements. So we can call what is given in the leaf nodes here, such as when you use the API, there will be some parameters you have to set, default values, and then you have to set them according to the data, and that will create a model. Is this the next slide? Yeah, we have to zoom this also. Okay, in classification and regression, can you come down please? Yeah, in perceptron, and then what is there here? Right, so this is forecasting, this is recommendation system. So for example, when you start with an application, you start with recommendation systems, such as what goes on LinkedIn. When we click a link and connect with somebody, there's a list of options of who else can we connect to. And how is this list made? Based on their skills and interests and their profile pages, which are passed by the LinkedIn recommender system engine. And that maps what we are connecting to and produces a list as a sorted order of things we can do next after doing this connection. So this is an example of application of machine learning. Time series forecasting on something like finance, stock market analysis, or this is on event detection in something like cyber physical systems. So one defines a problem in these applications and then goes back up in the graph which I have shown to decide the class and the class meaning the implementation detail and the algorithm design which we have to select for machine learning. So here we still don't know what is machine learning, but we are in a position to use it using Python. Okay, and then you have Gartner kind of agencies which do a market survey of all the companies and products out there using machine learning, AI and related technologies which are emerging, and then it is put into reports like this, this is a hype cycle where anything which is here has become stable and it has become mainstream and people are using it. Anything here is experimental and it's upcoming. So for example, this is a hype cycle for artificial intelligence made in the year 2021, and at that time things like responsible AI or AI governance or smart robots or knowledge graphs were upcoming topics, and things like machine learning, deep learning, semantic search, chatbots are stable topics. So if one has to set up a company or explore the products and create a solution in this area, one should look at these techniques and then do a deep dive into that, look at some application, look at all the keywords out there, put them into different categories of mind maps and start programming. But if one wants to do research, then one has to look at these kind of topics such as knowledge graphs and see where is it useful in medical domain, in finance domain, so on. So what I am covering will come under this category, something like artificial special intelligence. Okay, so here this is their framework to come up with the report. So first generation products need lot of customization, that's research. Early adopters must be needed to investigate. Mass media will create lot of hype, and then after early adopters apply those technologies, supplier consolidation will take place, then second generation technologies will come, methodologies will develop around that, and growth of these technologies based on adoption and innovation will happen. So this is their framework, Gartner's framework, to categorize the latest developments in AI. Similarly, we can categorize the developments in machine learning, in big data, in related technologies. Okay, so that's what normally people do. They do programming, they use a Python package, and they have to figure out how to use the API. But I'll give you a more mathematical formulation of the problem, where For example, we have to teach a machine learning algorithm how to add two numbers. Then what are the elements of our problem formulation? You have to give several examples like this, such as these 3-digit numbers plus these 2-digit numbers, this plus operation happening on scalars and then giving a result, and then this equal to, there is a left hand side, right hand side. So this is an example. This will be represented as a record. So this can be one attribute, another attribute, this is an operation, it can belong to another attribute, this is a equal to operation. After you do the calculation, then this is the final result. So 3 attributes and 2 operators, maybe 5 attributes we can put, and then describe this equation, this calculation. Similarly, all other calculations. And machine learning is data driven. It is not equation driven. If you know E equal to mc square, no need of machine learning. If we don't know E is equal to mc square or greater than mc square or less than mc square, E minus mc square is positive or negative. If we don't know these things, then we create data around these things, and then we hope that there is a pattern in this data. If there is no pattern, it's all garbage, then there is no machine learning, right? And that pattern, what is that pattern? That pattern depends on the addition here, which is based on decimal numbers and their position and position value system and how you add them, right? But we know how to do addition, so we know the pattern. There may be so many patterns we don't know. So we are doing exploration. So what is that pattern? This is where we build the model. So this is the next step we take after doing the application. So start with something like recommender system, use Python, get some solution. But what is it that solution is learning? When we get into that question, we want to know what that pattern is. So understand the concept. Provide various examples which are obtained from measurements or sensors. Okay? And once you know the concept, you can apply it on new data. This new data model has not seen, we don't know. In the future it is coming, let's say. But it follows the same kind of attributes, 5 attributes it can fit into that. Then you give that new data point as an input to the model, and this model can make the calculation and automate whatever thought process we have to create that calculation. And we can keep using this model forever as long as the data follows that way of putting into 5 attributes. Statistically, that distribution. If it follows some other distribution, then the whole story has to be repeated, which is we have to go back to the environment and get examples. Right? So this is the second step we can take after creating API based solutions. Okay. The third thing is this concept of PTE in machine learning, where the purpose of machine learning is to automate something and give some performance, such as accuracy of classification, some relevancy into the result which it is giving. And this performance is around a task, supervised learning, unsupervised learning, etc. And it takes in some data as experience. Machine learning is data driven. It is not like physics equations. We don't know the equation and we are doing exploration. So in this PTE framework, we have to formulate our mathematical problem and then do something like image classification, where this is the final API available to us, and then this requires some input data. So that input data requires all this data pre-processing, which includes, let's say there is a dog and cat image. You have to remove the background of the image, you have to detect the face of the dog, then break the face into eyes, nose and mouth. So all of this is a kind of a discretization process where we are getting the input which the model takes, and the output of the model is dog or cat. So we know the input and output, but we don't know what all these data pre-processing involves. So to be able to define this, we have to define PTE of each step in this is called a pipeline, each step which we take the data through and what sort of input we prepare for the model. So this is called a data pipeline. So data pipeline is the next thing we do after creating a solution, when we want to understand what sort of patterns are being learned by machine learning. Okay, so this is the next, after creating pipelines, if there are multiple pipelines, then how do we organize them? So this is the control pipeline, where there is a source database and we get these things called features for machine learning, and there is a training data set. So there is a process of training, testing, validation. We go through this process and we make this process happen for every step in the pipeline. So we are trying to control how different versions of pipelines are being created. So these features, these input attributes for machine learning, they are very important. If these are not there, then any sophisticated model can fail. And once you create that, we go through this process where we train a model, so-called training, where an algorithm is learning patterns which are not there, attributes which are not there in the database. It is coming up with new derived attributes. And after doing the training, we test it for performance, PTE model. And then we also do some kind of inference and validation. This is more performance testing. So this is the next step one would do for creating a solution in machine learning. Okay, and then I'll just leave these slides with you. There is a machine learning life cycle around data, learning, development, operations, etc. And we have to create a production environment which has all these steps. So this is one way to do it based on pattern recognition, where you can either study the context of the solution or the mathematical formulation of the solution. This is another one based on data mining, where this is the CRISP-DM process, cross-industry standard process for data mining, where you start with business understanding, data understanding, then go into modeling detail, then see how to evaluate and deploy the model. This is another framework which is based on the training, testing, validation kind of thing. So this is describing something I can't read. So, but I have taken this from standard resources. The idea is these are the frameworks of machine learning, and we have to put our solution into this to use it in the real world. So here there is description of raw data, learning algorithm, model, and evaluation and training, validation, test, inference algorithm, outputs, so on, right? So all these elements will come into our solution when we create some kind of a design or architecture around machine learning. Okay. And here are some examples of applications of machine learning, like recommender systems. So people generally ask what are the types of machine learning. So these are the types, for example, supervised learning, classification and regression, and applications are things like recommender systems. And there are different kinds of AI which are possible around that. So if you use a statistical framework, that's like distributions and samples, that's statistical AI. If you use rules, that's symbolic AI. And normally, typically we integrate different types of AI paradigms, and now we have to introduce deep learning, where we have to understand concept of a tensor. Tensor is a matrix, n-dimensional array, where it can be a rank 0, 1, 2, 3, 4 tensor. So here are diagrams. Rank 0 tensor is a scalar, rank 1 tensor is a vector, rank 2 is a matrix, rank 3 and so on is high dimensional matrices. So deep learning maps all problems into this tensor paradigm. Okay, so once we get into some sort of a framework for machine learning, we will see the need for deep learning. Okay, in deep learning, one designs things like, let's say neural networks, we are dealing only with that, and then the architecture of the neural network, the different layers in the neural network, algorithm for training the neural network, how the neural network learns patterns from the data, loss function, how many mistakes are allowed in the neural network, and explanation of how the neural network is arriving at its output given the input. So this sort of thing, we start thinking of this. So this is high level abstraction for any deep learning model. And then it is applied in problems such as classification, decision, ranking, detection. So detection is very important in cyber security context. This one. Explanation. You have to know why it is telling what it is telling, such as in a medical setup. You give a doctor a model and you tell this patient has cancer, you should tell why he has cancer. If I tell as engineer, I will tell my model is saying it has cancer, then patient will say as lawyer I will sue you, right? So there's more examples on the types of deep learning. So you have this one please. So these are different models for deep learning. So let's talk only about neural networks. So this is multi-layer perceptron, restricted Boltzmann machine, convolutional neural network, recurrent neural network, deep reinforcement learning, so on, right? So each of these models are being compared here, the pros and cons of where you would use it in a particular scenario of a machine learning solution, and then different feature types. This one, zoom. So you can have numeric data, binary data, categorical data, and then we want to analyze this in terms of the inputs which we are creating for machine learning. So which are like this. So for example, meaningful text from raw text, or changing data in temporal time series kind of data, or space wise changing data, or behavioral data in economics. So we want to get all these kinds of data sets and use the neural network models in a particular machine learning architecture, and then think of questions like this. Okay. Now that should be enough for us to understand what deep learning is and where do we use it. Now we come to cyber security. So normally you have a network kind of a situation where there is a list of possibilities for security which we want to check, such as data security, application security, system security. In the end, I have a IEEE taxonomy of different securities. So the application would be spam detection, phishing detection, or social network security, or cloud security, right? That is the application. So now we are getting into cyber security, not we are through with machine learning and deep learning, and we are able to use it anywhere. And in the cyber security, this is a systems perspective which we have to explore, where there are several types of security possible. And then now this has to be integrated with the machine learning lifecycle, the design, the deep learning neural network, etc. Right? So here's one way to do it. This is a adaptation of CRISP-DM, the data mining process, where you start with incident analysis. Why some security incident happened, and typically express it as some data set. Then move into modeling, but this is a security modeling such as data security, application security. Then look at data collection. Machine learning is data driven according to PTE definition, so data collection is important. And then further data transformation.
What is model fitting? Model fitting.
This one,
No, that. Model fitting. What is meant by model? Is that model fitting? Yeah, that works.
Hi, I'll get to this. We have to understand the overall process first. So this one please. So once we have some transformed data which can act as input to the model, and we can create some neural network out of it, then we customize it, we fine tune the model, and then evaluate it according to some statistical criteria, and deploy it in the real world application. Maybe on future data also it must work. And then we keep doing this iteration again and again until our solution works as expected. And if it does not work, then we see why it is drifting from where we are. Okay, I can talk of this. So like I said, we have to create the training data, which is, there is an algorithm which is going through some data set and it is learning patterns out of it. So that data may not be readily available to us. We just have some images or text. From that we have to get this data, which will involve all those features, etc. I am talking of. Now this training data will be used to create a model. Model is algorithm plus parameters plus learning environment plus training procedure plus so many things. Now this model, how you create this model statistically is the model fitting. So the model should neither underfit nor overfit. It should just learn the pattern which is there in the data, and it should not provide too complex pattern which is not there in the data, or too simple pattern which is there in the data but not detected. If it does that, then we can expect model to go make mistakes on new data or even on given data. I have given it 100 records and it is learning some simple rule, some linear rule, saying if this happens, if this attribute has this above this threshold, then this is the output. But then I can always find a counter example where that threshold is not met in that set of 100 records, which the model has not learned. So if the model is supposed to be 95% accurate, then it will start making mistakes. So this is the case of underfitting. So similarly, there is a case of overfitting. Model is too complicated. It is giving some very fancy math and then it is telling my output is dog or cat. So I would say, why do you require so much of complicated processing to tell dog or cat? If you have to tell different species of dog, or dog apart from a wolf, or cat apart from a tiger, then you do all this fine-grained kind of processing. If you just hit a small nail with a big hammer, then there is no use of that small nail will break. That's not the purpose. But I'm just giving a very simplistic explanation. In statistics, there is this concept of fitting a model and tuning a model, where what is a model around an algorithm, and how to evaluate the model, how to use it. This is being described. So once you create the model, there is a model available. Now no longer we look at the data, we just look at the model. And on new data, which we have not seen, test data, which will come in the future, let's say, model must work as expected. This is the gold standard which the model has to meet. If it does not meet this, then we have to go back here and then check something's wrong in our thinking process. If it works, then one can come up with validation data and other data samples to keep checking that the model works as expected. So this is all part of model tuning. And here I have shown some learning curves where the loss function, what you are using to make the calculation on the prediction, is being plotted against some parameters and changes to those parameters. Now this loss function starts with a high error, then there is a decrease in the error, and we don't want overfitting or underfitting, not too complex, not too simple, just right. In this area, for different data samples, we produce these curves, and these curves must be closer to x-axis, closer to 0, y is close to 0. Then the error is less, and we can claim that model works. Okay. So this is what we have to do for every cyber security application, right? This process, and then this sort of mapping, and then this data set sample analysis, and then these learning curves, and then evaluation. Okay. Okay, now I'll get into adversarial learning. So adversarial learning can be machine learning, deep learning, both. Adversarial machine learning, adversarial deep learning, adversarial artificial intelligence. When it's applied in cybersecurity, it becomes adversarial AI. Now this is an example in spam detection where there is a filter in your Gmail inbox telling apart ham from spam. Ham is the email which you check, blue email. Spam is red email. Somebody, some attacker, it could be some random noise, or some attacker wants to target your mailbox. So what is the purpose of this filter? To get more blue into your inbox and more red into the spam folder. Now how is this filter built? From email data. This is available somewhere. So in Gmail, Google has taken this text data and then created this filter. Now there is this intelligent attacker, China, who wants to target your mailbox because you are minister. Now this China also has access to same data that Google has access to, and it analyzes that corpus of text to come up with some contaminated data to mislead the classifier. That's the end objective. Not to make the classifier, the P here is not to make a highly accurate filter, but the P is to create as many data samples as possible to make the filter go wrong. But it will be hard for us to detect that it has made a mistake. So the misclassification is the focus for this attacker, China. And this attacker looks at this two label classification problem and comes up with their own way of interacting with the filter and new records which are not there in the original distribution, but they look like the original distribution, and then these records, the attacker first tests them out and says, okay, these things, this spam looks like ham and this ham looks like spam. Now I am going to send this to the filter. When this happens, and if the attacker is successful, your mailbox is filled with spam instead of ham, and you cannot use the mailbox for its intended purpose. Now the same thing can be generalized to several cybersecurity scenarios. Okay, and attacker can have, in terms of machine learning, these objectives. They can try to influence in terms of classification the true positives or false negatives, or true negatives or false positives. So true positives will become false positives, or false negatives will become true negatives. So how the confusion matrix is being manipulated is described in this table, where attacker can just explore. They don't have access to training data, they don't have access to model or algorithm, they just have access to test data, and they keep sending test samples which will make this happen rather than this. So that's exploratory attack. Similarly, attacker can look at the data distribution underlying the training, testing, validation, etc. samples which we have. So that's called a causative attack, and in that attacker can target particular class label, such as I want to make spam look like ham rather than ham look like spam. So you can think of other scenarios, more real world scenarios where this has application. But I'm trying to introduce the machine learning from the cyber security perspective. So there is exploratory attack, there is causative attack, and then there is this CIA, confidentiality, integrity, availability, which can be affected from the data which the attacker has created with respect to the model which is being targeted. So here there is a definition. So for example, integrity results in intrusion points being labeled as normal points. So this will be the attack objective in terms of machine learning oriented cyber security. So one has to note that cyber security like spam detection is independent of machine learning, right? But where does AI fit in here? And does it improve things or make things bad, or what are the pitfalls? So to be able to do that, we have to see the objectives of that AI, right? Now here's another taxonomy where this attacker is also called adversary in the literature. Now that adversary can target data, where I gave example, or algorithm. In case of algorithm, adversary can create features or target the classifier. So let's say it's a supervised learning problem. In the classifier, the type, architecture and parameters of the classifier can be targeted. So very deep dive into the model, adversary can go and decide which part of the learning must be targeted. Now this is also given in this iteration here, where there's an adversary playing sort of a game with a classifier. Classifier is our filter. It is doing this. Adversary is creating a learning environment which is different from its normal environment for the classifier. How does the adversary do that? By going through these steps. First is analyze the classifier for all these things, data, algorithm, etc., these objectives. Then devise an attack. Create data which looks where spam looks like ham, right? This is the simplest kind of abstraction we can have, right? Now this attack may be successful or fail. If the classifier does not account for this attack, then it will definitely be successful. So the classifier has to account for all these scenarios in its training and then develop countermeasures, such as adding new attributes, retraining the model, right? And then deploy the model again, attacker again repeats the procedure and then keeps interacting with the classifier indirectly or directly, and then classifier has to adapt again. So this goes on endlessly, like a Cold War type arms race. So this is US and this is Russia, and then they are fighting with each other, making nuclear bombs, right? So something like that in terms of AI is happening. So this study of this area is adversarial learning. Now where does deep learning fit in here? There are different scenarios for attack in the cyber security applications, such as in the spam detection. And these scenarios can be mapped as search procedures. Now if this is a non-guided search, such as a random search through the search space of all possibilities in the data attributes, that's one way to search. If it is a guided search with particular objectives, objective can be created as an optimization objective, and different types of algorithms can be used for that, such as gradient descent, where the first derivative of the optimization function is used. Twice differentiable, something like Newton's method or variations of it, or non-differentiable, something like genetic algorithms can be used. So here, this is being created as a technical problem for the adversary rather than some random search, and the solution of optimization, which could be global, local optimization, non-convex, stochastic, etc. optimization, is being used to create the adversarial data set from the training data set. Game theory is an abstraction for all this. How to do this differentiation, how to do the optimization, what are the optima solutions, can be expressed using this game concept coming from economics, made by Nash, who got the Nobel Prize and then went crazy. There's a movie on him. So the game, like in reinforcement learning, there's a search space in which the game operates. I'll not go into that, but I wanted to tell you that targeted search can be done on the training data set to come up with different scenarios of attack in different cyber security application domains. Now, these scenarios are further put into different taxonomies in the literature. Here's one taxonomy where stage of attack, training or testing, attack conspicuousness, the target, and I can't read this, but the modeling knowledge, goal of attack, where, for example, white box, black box, gray box. What does the adversary know in the previous diagram? What does the adversary know about the classifier? The entire architecture of the classifier, just the training data set used by the classifier, the features used in it, the distribution underlying it. So that taxonomy is put into white, black and gray. In black case, it's a black box. Adversary does not know anything about the classifier. And then he just has some access to some public data, and such as China has access to public data on the internet or on a mobile phone, and then they are targeting some nuclear plant, coming up with some changes to the data. That's the hardest thing to do, because so many possibilities are there. White box is the other extreme, where everything is known. So let's say our minister starts using Gmail and China hacks Gmail. So everything which the minister has corresponded with other countries is known to China. And then what would be the objective then? And something in between is gray box. This is more realistic. So similarly, there are other kinds of taxonomies such as goal of attack, so on. Okay, and now this is called, this is a way to combine all the different scenarios there. This is called advanced persistent threat. It has these different stages such as reconnaissance. This is like from military domain, defense kind of terminology, where how can you weaponize data, such as using deep fakes, and how would you deliver it, such as with phishing, and what is the intrusion objective, where is the command and control, army headquarters, and lateral movement, get into a network, then affect the software, combine spam with phishing with malware, and data exfiltration, get sensitive information such as president's location out of the system, right? So to be able to do this, there is this kind of intelligence terminology which is used, things like social engineering, spear phishing, which are being combined with malware, phishing, spam, and it's a kind of a hybrid scenario where multiple things are being tried out. And all these kinds of scenarios are possible as an optimization objective. Now, unless you have counter scenarios like this, such as patch management, firewall, and malware detection, and security event management, anomaly detection, data loss prevention, data governance, etc., definitely the machine learning model will fail. So you bought a new car which is going to drive on its own, it will not drive on the road, it will go off the road. And your investment in the car is wasted. And China wants this, right? So, or whatever military scenario where this kind of thing is applied. Okay, now this is my last slide on theory, where these are some learning theory frameworks one can use to analyze adversarial learning and its deep learning, etc. variations, such as this one here, where the objective is to learn a target function f mapping a x to a y, such as in supervised learning, x is the data given to us, y are the labels which are output, f is the function which is unknown and we are learning through the model. Training examples are given to us. Here's an example of credit score is given here, where let's say there is a bank manager deciding whether to give a loan to a customer based on history of previous customers in that bank, and that history is the training examples here which we have. And there is an algorithm telling the bank manager through some interface that okay, this customer can be given in this slab this much loan for this duration with this interest rate, etc. This is based on an exploration of the data set using concept of hypothesis, statistical hypothesis. So many possibilities are there. This customer is a rich customer, is a poor customer, is a South Indian customer, North Indian customer, is an NRI customer, so on, right? So all these are the hypotheses, and there is a search space of hypothesis which is being gone through. These are all the candidate formulations which the learning algorithm can go through on the data set and then come up with a final hypothesis G, which is approximating the F which we want to learn. It's always approximation, it's never equality. If we know equality, this is physics and maths. So we don't need machine learning. and we come up with approximate solution and then give a decision to the bank manager saying, okay, this customer can be given this loan for this duration and this interest rate and so on. So we convert the statistical hypothesis in terms of the application domain terminology. So similarly, now this is called PAC learning, probably approximately correct learning, and the objective here is to learn the target function. Now this target function can be mapped to the machine learning, deep learning, adversarial learning, and its application in cybersecurity or any other application for that matter. So that's one framework. This is another framework called mistake bounds model, where there is a learner classifier cluster model, and we want to decide how many mistakes can the learner make before it learns the target concept. This is the big question we want to answer. Now this target concept was a function here. If we don't know this function, such as in reinforcement learning, then what is that concept and how many mistakes are tolerable? And how do you put this framework into all the previous frameworks? That comes under computational learning theory. Here's one way to do it, where there is this concept of sample complexity. How many training examples are needed to learn a successful hypothesis? We want to answer this question. And the answer to this leads to a less computationally complex model. We want less complex, not more complex, but which still does the work. So similarly, how much computational effort is required to learn a successful hypothesis? Time and space complexity. Mistake bounds is combination of these two. How many training examples will the learner misclassify? Misclassify, not classify. Classify is already done. This is advanced classify, which is misclassify. How many misclassify okay before converging to a successful hypothesis? So this is a mathematical formulation of the previous interaction I showed between the adversary and the learner. Okay, similarly there are many others, and all these are used in defense mechanisms where we come up with adversarial learning algorithm which may involve deep learning. Okay, now these are examples of adversarial data in different application domains. So we are getting into cybersecurity. This is an image classification where this is handwritten digits. If you look at this data and this data, there is some blurring here, some dots here, and then the classifier, typical classifier such as a convolutional neural network, CNN, normally it has to predict this as 3 by looking at the pixels. It predicts it as not 3 if you just blur it somewhere. But which way to blur? Blur here, blur here, blur here, add something here, here. That we have to figure out. That's the adversarial data. So you add adversarial data to this, you can mislead the classifier. This is in image classification of handwritten digits. This is in image classification of different cat dog kind of scenarios, where here's a panda, derivative of the panda with respect to a loss function on some parameters just looks like noise. Add this noise back to panda, panda is called a gibbon. You can make panda as a monkey, as a tiger, as a truck, as anything you want, right? So this is another example in image classification. Here's another example where there is a turtle. Now based on this color coding, this turtle is classified as rifle, okay? And then this turtle, green turtle, is classified as turtle. So green is, I think this. And then this black is classified as something else, this black here. This black is something else. There is no green here, all red. So when we look at it, as human beings, when we process this information, we can make out it's a turtle. But the way the model is learning the patterns and how the machine intelligence is happening, it thinks it's not a turtle but a rifle, right? So this is another example. Here's an example of stop signs, traffic signs, where there is a self-driving car made by Tesla going on the road, which is very nice, not Indian road. And then there are all these stop signs or go signs, which is telling the car, there's no driver. It's just a camera taking data stream of images and deciding whether to stay on road or go off road. Now here there are different ways to different angles of the camera and different patches you can put, like there's this black patch here on the below the stop sign, and then there's a white patch here. Different ways you can change the input to that car to make it go off the road. So it does not do what it is intended to do. So it is malfunctioning and the performance according to machine learning is not happening. So first we have to create these scenarios and then we have to defend against these scenarios. And it's never ending. So this is in image classification. Then I had something on text and so on. Okay, so these more images. Researcher with virtual glasses called actress. Researcher plus Putin giving order launch nuclear weapon. Obama, person talks, Obama photo talks. Face of the actress replaced with another person's face. And here there is a truck with the perturbation and adversarial truck. There is a temple, perturbation, adversarial temple. So these are all images where you can obtain this image, for example, from Russian government website. And let's say this is hacker. Hacker is saying something, appears as if President of Russia is saying something. This is not a real picture, but this is created from a real picture. It's called a fake picture. It's called a deep fake. And you can create several such fakes. Researcher, when we look at it, is a researcher. But model thinks it's an actress. Right? Here, face is being, so particular image processing is being done on the images. And so on, right? So there are variety of possibilities in which we can create fake data. And all your Facebook information, mobile information which is there on the internet can be used for this purpose. Right? And you can think of the objectives of the attackers or adversaries which may be malicious. Okay, so this was, similarly you can create adversarial data on different data sources such as text, graph, tensors, so on. Here's there's an example of phishing detection where, can we zoom this please? This one. I still can't see. Okay. So this is from the body of email. What sort of data can you analyze to create a phishing email or a countermeasure for that? So these are the features for machine learning where you can have lexical tokens or topic in the body or part of speech tags, named entities, vocabulary, some features such as urgency or threatful language, URL features, HTML features, image features, sender information, phishing, commonly used phishing terms, term frequencies, size of email, JavaScript input, so on, right? So all of these things along with this metadata such as received from, sent from, delivered to, subject, timestamp, mailer information, so on, right? So all these features can be used in to create a phishing email. And can you come down please? This is the process which a phisher will go through, where these are different phases of phishing. Attacker can be different types of attackers. This is just some random individual, or serious hacker, or organized crime, or terrorist, or state actor, right? So this person is going to analyze all those features to create an attack scenario. And target is what? End users, financial services, retail services, internet service, etc. Right? And here we go through that kind of data security, application security, all that stack, and then see all the vulnerabilities where you can target either authentication, authorization, or software or hardware or network or any sort of loopholes which are available to achieve this objective, such as steal money. And there are advanced things such as deception and intelligence gathering. All these kinds of things can be added with the phishing email, and this can be done automatically with a genetic algorithm on the other side, with a multi-agent system on the other side, or by a person, or by a program. And then you can affect the identity of a person, take the money from the person, affect their reputation, affect their life also. Now, these are the phases one goes through in phishing to create the adversarial data using machine learning. And what sort of information do you have? Any public information, email address, mobile number, etc. And what sort of data is created? Deepfake type data. And the mechanism of delivery will be your e-banking solution app which you are using in the phone. And different kinds of malware, phishing, botnet, etc. can be mixed here. And then further some inference can be added around the credentials, authentication, authorization, and then illegal use can be used. Information found can be sold, it can be used for espionage on other countries, so on, right? So a simple phishing email can do all these things using machine learning. So here's a Microsoft taxonomy of all possibilities where phishing can be used, AI driven phishing. Still not visible? No, some more. This is the maximum? Okay. So this is basically a categorization like the APT attack which we saw, where you can create different scenarios combining things. I'm not sure if you can read the headings here. These are the different categories which Microsoft has identified. And then, yeah, so you can affect the pre-trained ML model or ML model with which has been saved, or you can create evasion attack or inference attack on the model, and then you can do it at deployment stage. You can use it for exfiltration, right? And then here the combinations are phishing, traditional software attacks such as a virus attack, and then implant something, and so on. So you get the idea. So this is basically a hybrid type of a scenario created by a corporate company to develop their products. Now this is a research type of scenario where the objective of phishing can be white box, black box, etc., targeted, untargeted, etc., single model, cross model, character level, word level, sentence level, etc., or different types of neural networks such as CNNs, RNNs, autoencoders, etc. So all this modeling detail can be used to create adversarial attacks on deep neural networks used for text processing of the phishing data, for example, phishing from non-phishing data. And here the applications in NLP are machine comprehension, POS tagging, relation extraction, OCR, image captioning, speech recognition. So for example, you can combine image and the textual description of the image. Both of these can be combined in deep neural network, and on the combined representation data you can come up with these attack scenarios. And then not only the learner but also the attacker can use reinforcement learning or any of the learnings, generative learning, discriminative learning, right? Okay, so this is in malware. So we saw two examples. This is another on malware, where how does malware work? There is a filter created, there is a manual analysis, there is extraction of attributes in data, there is signature created to decide whether system is infected or not, and this is the process of malware. Now, what does AI powered malware do? Zoom this please. This. It can do adaptation, it has autonomy, it can do automation, it can do augmentation. So it can adapt to environment, it can use prevailing data, it can do reverse engineering and targeted attack, it can go cross platform, adversarial attack, poisoning, evasion, inference, etc. attacks, it can steal the model, it can do optimization based on swarm intelligence, evolving malware, and then mutate the mutable malware, so on, right? So all this is new sorts of malware where AI is being combined with the traditional process of malware. Okay, this one please. Now here's a GAN which is generating malware on its own from raw data. There is malware, there is noise, it takes as input, there is benign data, there is a generator and a discriminator. These are playing a game against each other. So generator at the end of the game is able to create adversarial malware examples in a black box scenario, and this malware can be used with or without labels on any detector. And this detector, because it's a black box, the original detector is not known, there is a substitute detector which is made, a rough approximation of the original, and here you can generate malware. And this one please. Now these are different ways of generating data using deep learning. So this is adversarial deep learning attack in malware, and you can either specify the explicit density that are such as 1 by root 2 pi sigma e power minus x minus mu square by 2 sigma square, something like this, for a multivariate Gaussian distribution explicitly, or implicitly just giving it training data, and then it learns the GAN which I showed is able to learn the distribution of the data and come up with malware changes to the distribution. And in explicit distribution you can have all these types of explicit equations for the distribution. These can be exact or approximate. In approximate you can have things like variational autoencoders. In implicit density you can have GANs. So both of these are deep neural networks which can be used to create malware data. Okay. So this is another example where you have botnet. Bot is a robot which is sitting on a network and is able to affect it, and it is used in a variety of scenarios such as intrusion detection system. This is the process of botnet, where there is a bot master affecting a command and control server. There is an initial infection, there is a mutated secondary infection, and there is a victim whose data is being stolen. Okay, and then this one. This one, sir. So these are the different types of malware botnet detectors, such as in an IDS system, and it can be based on signature or anomaly and so on. There are things like HoneyNet, which are hybrid, and in the anomaly you can check the protocol data of the network, or you can check another machine learning derived data, and all of this can be used to create the botnet. So this is how botnets normally work. Similar to malware, except it is evolvable. Okay, this one. So one has to create a table like this for evaluating the various botnet detectors out there, such as in cloud-based services, authentication and authorization which is being done, and whether the usability, efficiency and robustness and privacy of the model is preserved or not. These must be decided by the defender of the model. Okay. Similarly, there are other types of models here. I have listed a very exhaustive list of models. Okay, and then there is one more below this. Below this. Okay, there is nothing. So this is on botnet. So this is how you evaluate this is there. So this is how you evaluate your botnet detector, and this is how you create a solution for the botnet detector. Okay, so here the phases are, so user profiling, deep neural network reconstruction, then here data cleaning and segmentation, physiological and behavioral features, deep learning based authentication. Different layers, activity recognition, user behavior recognition, for everything there will be a neural network. All of this must consider the different scenarios in addition to the botnet detection scenario. So this is actually, you can see, very complicated. Okay, the next slide. Okay, so this is on IoT. So Paresh already talked of this, I'll skip this. Next one. Okay, this is more on authentication authorization, where we have to think of the attack and defense and the performance metrics associated with that, the data set and the end task which we are doing in the adversarial deep learning. So here are different evaluations to do that based on, so let's say, can you zoom this please? So lightweightedness, heterogeneity, availability, scalability, early detection, energy efficiency, deployment flexibility, all these are requirements of the authentication authorization model. And these are applied in application layer, network layer, physical layer, etc. They will involve different tokens such as user credentials, and they can be centralized or distributed, and they can be based on a certification mechanism or blockchain mechanism or hardware driven. So all these system theoretical aspects come into the algorithm and model design to be able to create a robust authentication mechanism which is able to withstand the adversarial attack. Right? Okay. Similarly, there are other ways of evaluating. Okay. Okay. Next slide. Okay. So maybe we'll see this. So here, yeah, this one, this and this. First this. So this is open source intelligence. This is advanced persistent threat. This is hybrid scenario. Open source intelligence which is being combined with social engineering, phishing, physical access to get into the kernel or port or as user into a network, and then the end objective is data collection or physical damage. And here there are different stages it goes through. Open source intelligence and its analysis is reconnaissance. Then initial compromise is just something like phishing. Then privilege escalation is you impersonate users. Then lateral movement is get into network, get into then hardware, database, etc. Then mission completeness is do the damage, physical damage to critical infrastructure or get sensitive data, so on. This one. So here is the same on the rows, and these are the different scenarios which are possible, such as SQL injection, cross-site scripting, lateral movement, data tunneling, side channel, steganography, cryptography related. So all of these things will be combined with these things such as direct inspection, complete inspection, event based approach, flow based approach, hybrid approach, etc., etc., right? So this is what typically a nation state would be doing in combination with all these stages to do this one please. To do the states and belief updates like this. So the reinforcement learning type states, there is a legitimate and adversarial user who is updating their beliefs about a system by interacting with the system in k stages, and there is imperfect information available about the system. The defender is also updating their beliefs, and the defender is sophisticated or primitive based on suspicious actions, and this goes on repeatedly for k number of iterations. So this creates a reinforcement type hidden states kind of scenario. Unless this solution is there, nation states can get into critical infrastructure. Now this is the game theoretical model of this solution, where you have this zero sum game. I will not get into games, but you have zero sum games, you have non-zero sum games, cooperative games, stochastic games, differential games, etc. Now there, that game has no information about the target or has information about the parameters of the target, such as cost, utility of the target, and this information is based on ground truth, which is your predicted data, or on input data, some probability distribution which is being learned. Okay, and this information is used to create, so this is sequential, Bayesian, non-zero, etc. games with the target, and the resulting attack scenario can be exploratory or causative or combined or hybrid and so on, right? And finally your spam filtering, etc., stock price prediction, etc. is being targeted. So these are real papers which have used this kind of game theoretical modeling to create a APT attack. Okay, so that's all the attacks. I have given a flavor of the attacks. Now just 2 slides on defenses. Okay, this is more on reconnaissance. I think we can skip this. And then, okay, so there is this concept of TTP, technique, tactic, task. Okay, and we have to understand these TTPs on the attacker side, such as cache poisoning, public disinformation, clickbaiting, so on, right? Some of these are made to make fact appear as fiction and vice versa, and this TTP we have to understand. Okay, here. This one. Okay, red teaming is one way to deal with this, where there is a concept of blue team and red team. So like what I am doing, all this analysis somebody will do in an organization. Blue team is people, members of that organization, such as people sitting here. And red team is somebody like me. And that red team will have domain knowledge. They will have computational representation based on machine and human data. And they will do simulation of the scenarios and create optimization around the modeling and create a learning around that. Theoretical, practical learning such as game theoretical learning, multi-agent system learning, reinforcement learning. And finally show some report to the blue team saying this high dimensional data has been analyzed in this virtual environment over this fitness landscape in this multi-objective optimization to create this kind of adversarial learning and its evolution and self-organization, etc., around that. So this sort of a solution a red team does using computation in an AI sense. So that's called computational red teaming. There are red teams which don't use AI also, which is the traditional way of doing it, but only AI can counter AI. So all this is required. And then you have now job roles such as AI enabled penetration tester, security planner, network defender, etc. All of them have to understand adversarial attacks, autonomous agents, defeating AI agents, and then for that they have to do all this kind of modeling, combining human and machine data such as threat identification, situational awareness, and threat evolution, autonomous learning, generative learning, etc. Right? Okay, so this is one, red teaming is one kind of defense. Another kind of a defense is you put the attack types into a search space like this. So here this is a machine learning type of a defense where this one, please, this graph. What sort of information does the adversary have? That's what we are trying to model. Hardware implementation architecture, inference data and network architecture, neural network architecture, hardware plus architecture plus data. So these are possibilities. Target is confidence reduction, misclassification, targeted misclassification, source target misclassification. And in all of this, you see where is the attack strength, what is the hardest thing to solve, and you create a learning model for that. Okay, this one please. So these are sort of the gaps which we identify in machine learning models, and we come up with new models which can do learning in complex environments, in resource constrained environments, and can do generalization and prediction with explainability, and they can be integrated into existing quantitative models. So in a deceptive environment. Okay, so this is the machine learning kind of a defense, and the simplest type of defense, the panda example which I talked about, it's defend against the derivative of an image. So you have non-differentiable, differentiable, and then come down please. Then you have twice differentiable and game theory. So all this is a description of these techniques. These game theoretical type models are able to create defense mechanisms into different cyber security attack scenarios. Okay, so these are the latest state of the art methods. So you can either add to the training data, you can change the machine learning model, you can let the not adversary get into your network, and then down please. You can create adversarial samples and specialized detectors for those samples. So again, more description on that. So this is a machine learning way of defending. Okay, so crime can be crime for hire, cloud as a service, crime as a service. Okay, so yeah, just the previous slide. Okay, so you can have a shadow broker, you can do phishing as a service, ransomware as a service, and malware as a service, and botnet as a service, all these things. You can hire people on the internet to do this. And now these people's objectives must be mapped into more graphs like this. So supervised learning, reinforcement, active learning, classification, clustering, association, rule mining, dimensionality reduction, etc., etc. Which of these models are most at risk? We can analyze. So as we go from supervised to reinforcement, there is increasing autonomy to the model. Here, I think in below. Okay, it's not there. Okay, so these models are least at risk, and these models are most at risk. Something like unsupervised active learning models, something like reinforcement game theoretical models, least at risk. So we can analyze the models which this crime as a service provides, and then create defenses around that. Or this one please. Or you can look at the complexity of the model. What sort of information adversary has, architecture, training data, and then there is different samples, and then this oracle concept, knows everything. So knowledge of the adversary, and then target of the adversary, adversarial goals, confidence reduction, target misclassification, etc. What is the most difficult attack? So this sort of a thing must be created. Okay, so here's an IEEE standard, just last slide, previous slide please. Okay, so this is an IEEE standard on the different types of security which is there: data, software, component, connection, system, human, organizational, societal. Now for all of these securities, the competencies which have to be built into the solution is resilience, conflict management, communication, teamwork, attention to detail, etc. Now this is what skills people have to acquire, and this has to, the stakeholders here are enterprise architects. Expand this please. Public policy, enterprise architecture, organizational security, software development, management, procurement, all these are stakeholders for all these different types of securities. And here's more examples, this one please. On the various applications which come up as a result of mixing machine learning, deep learning with cyber security. In data security, things like cryptography, authentication, authorization, cryptanalysis, tag analysis. Then software security, design, implementation, analysis, testing, deployment of the software. Component security, component procurement, testing, and reverse engineering. Connection security, physical media, hardware architecture, network architecture, and say system security, systems thinking, systems control, systems testing, system architecture, human security, intelligence, social engineering, and social and behavioral privacy. Then organizational security, risk management, cyber security planning, so on, procurement, so on, so on. And then societal security, cyber crime, cyber law, cyber ethics, cyber policy, privacy. So all these aspects come into play when we combine machine learning with cyber security. I think that's it.
Thank you, sir, for your great presentation. And we really powerful such kind of presentations from in the future. Now I request Dr. Rashidhan, sir, to hand over this afternoon to Dr. Aneesh.